Hey everyone, so this is the beginning of the very last unit as far as AP Physics is concerned, where we're going to talk about rotational kinematics or rotational motion. And we're going to start with the concept of rotational kinematics. Now, really quick, I do want to point out that I had mentioned this before that for the most part with this topic, we pretty much almost recover everything that we've talked about so far, all the units. So keep that in mind as we go through this. Uh, Note that there is a lot of new terminology, new symbols that you have to be aware of. But if you listen and pay attention and relate it back to what we've done before, it'll make the whole topic a lot easier for you to kind of comprehend and take in. Right? So the first question that I ask is, conceptually, is how do we know an object moves? Right? Let's go back to the beginning. How do we know when an object is moving? Well, if we think about it in terms of, kinematics, normally talk about how an object is displaced from one point to another. If you take a snapshot of a scenario, of a room, and you take the same snapshot again about an hour later, and you see that something has been displaced, you know that that object was moving, right? Now, here's the question in this scenario is this object moving? Now, you might be thinking, yeah, of course it's moving. I know it's moving because I can physically see it moving. However, if we use our understanding of motion based on unit one, this technically isn't moving because it's not being displaced from one point to another. If I take a snapshot of this and then an hour later take a snapshot again, then this object hasn't moved left, right, up, down. So it hasn't been displaced. How do we know it's moving? Well, what we have to do is change our definition of motion to incorporate rotation. Everything that we talked about before never really took into account rotational motion. It was referring to what's called translational motion. Translational motion is the concept of the object moving left, right, up, down, pretty much, within the physical space, while rotational is the object is staying in that same physical spot, but rotating around in that. So we had to come up with a new definition for displacement in this scenario that makes more sense. Because again, our displacement is, thinking about it in terms of that translational idea. So what we now have to do is talk about rotational displacement, or what we call angular displacement. Basically, when an object is rotating, we can talk about how much it has been displaced by how much it has rotated, right? If we imagine that there was a point on this sphere, right here, and then it got rotated to this point, well, we can ask ourselves, well, how much was it rotated? So angular displacement is going to be represented by this theta, and it's going to refer to how much the point has rotated along in that rotation. One thing to keep in mind is that angular displacement is measured in the units of radians, not degrees. So when an object goes from this point all the way around, that is not 360 degrees. That is going to be 2 pi radians. All right. So pi radians is going to the other side. Half pi radians is a quarter turn. If you do, 2 turns, that's going to be 4 pi. That whole shebang, right? So this is angular displacement, and it's our first kind of rotational motion type of concept. Now, one thing in math that you should have learned at some point is that we, instead of all talking about how much the point has rotated angularly, we actually can talk about how far the point has actually moved. A good reason for why we would do this is to imagine something like a person standing on a carousel, right? Not only has the person rotated along with the carousel, but they have physically moved from one point to another. So we can also talk about the translational motion when an object is on a rotating surface. So the equation that we use is using this: S equals theta r. Uh, S in this case just represents linear distance. Technically, you could replace this with x. The only reason I left it as S was so that it matched this diagram, but also it matched the equation that you should have learned in math at some point. But this is really just linear distance equals the translational distance times r. Uh, if we think about it in terms of units, this makes sense because s is the linear distance, and we know that linear distance is measured in meters. Theta is measured in radians, which technically doesn't have a unit. Normally, you don't actually have to write radians next to the number, though I still highly recommend that you should. But this angle doesn't. This angular displacement does not have actual units. So in order to have this equation balanced out unit-wise, we have to multiply it by another uh, meters, the radius in this case, in order to have the equation make sense. This is one thing to keep in mind with a lot of these equations is that for the most part, a lot of these translational to rotational equations like this, where you can take a rotational equation or a rotational variable and turn it into a translational term. The equation will always have them on opposite sides of the equation, and then you just have to figure out where does the r go, and you kind of figure that out based off of what makes sense with the unit. So while a lot of these equations are on the reference table, so you don't need to do this, it can be helpful for you know thinking about it on the fly and just kind of doing that, or some of the other slightly altered equations that we have. I'll mention that more so in class. So here's the first question. Pause the video, works up, and we'll go over in a second. All right. So the first question, we have an object on the Earth. It rotates with the Earth for one full day. The first question is, what is the total angular displacement? Well, again, we're on a rotating object. We rotate in one day. The Earth rotates one full time. Therefore, it's going to end up being 2 pi radians for the angular displacement. Now, to find the total distance, we are going to use that equation. In math, it's called the SOAR equation. But we're just going to take this angular displacement, times it by the radius, and we end up getting 4 times 10 to the 7 meters. So again, you have rotated with the Earth 2 pi radians, and you have also traveled a physical distance of 4 times 10 to the 7 meters in that one day. All right? Now, we could ask ourselves, well, is this the only thing that we talk about? No, because if we look at these two tires, we could ask ourselves, well, what is different about them? Well, they are both rotating, so they are covering angular displacement, but just like how we have it in linear terms, in translational terms, the rate at which they're rotating is different. So we could talk about the rotational speed, how fast or the rate of change of this angular displacement that the object is experiencing. Angular velocity is going to be represented by this symbol, which is an omega symbol. The omega, or angular velocity, represents the rate at which the angular displacement changes. Note that if you just replace the word, or just get out the word angular in this definition, it literally is just the definition of velocity, right? Velocity is the rate of change of displacement. Angular velocity is the rate of change of angular displacement. This is one thing I mention to my students all the time, is that half the time when you're doing a rotational kinematics question, what you can do is ask yourself, replace all the angular terms with their linear versions, which is a lot of times very easy because they just tack on the word angular half the time. So you just block out the word angular or any of those angular terms. You can ask yourself, what equation would I use in if this was a linear case? If I'm given velocity and displacement and I'm looking for time, what equation would I use? Well, turns out that you're going to use the exact same equation, just the angular versions of that, right? So the unit for angular velocity is measured in radians per second. And okay, so we'll get to the equation later on. So let's worry about this. So the question goes, let's say that we have these two objects, these 2 points on a disk. The disk rotates one full time. It doesn't do it right here, but it rotates one time. How do the angular displacements compare? The linear distance compare? The time and period compare? Angular speeds and linear speeds. Well, if we go through all these terms, the angular displacements are going to be the same, right? After one full spin of this wheel, this red point and this blue point will return back to their same point. So they have both been displaced 2 pi radians. So their angular displacements are going to be the same. Linear distance, though, if we think about it, because of the fact that this is further this red point is further from that center point, the distance it's going to travel is much longer because it's traveling a much bigger circle than the blue point does. Right? Yeah. So that wasn't supposed to turn. Oh. Uh, So this red point is going to travel a much greater linear distance. What about the time and period? Well, again, they will get to that point at the same time because they're on the same physical disk. So the time and period will be the same. So how do their angular speeds compare? Well, according to this, since their angular displacement's the same and the time is the same, then their angular speed should be the same. But the follow-up question, how do their linear speeds compare? Uh, Going back to here, because this one is traveling a much longer distance in that same amount of time that this one is traveling, this one is going to travel at a much faster speed, right? So, um, yeah, this kind of goes through the concept that I was just talking about, how the red dot is going to travel a longer distance, so it's got a faster linear speed, even though their angular speed is going to be the same. So the equation that we have for angular speed is this. Omega equals theta divided by t. And omega is going to be measured in radians per second. And sometimes you might be given units in revolutions per minute, and that means that you're going to have to convert. Uh, Remind me, and I'll show you in class because I do want to kind of go over that quickly. It is kind of weird, but it's just more of replacing what the word revolution means and the word minute. So it's not that complicated, but it takes a bit of time to show. Um, Now, one thing I actually did want to mention that I haven't said in here is that all these terms are technically vectors. So the object can rotate either clockwise or counterclockwise. Um, Conventionally, I think it's counterclockwise is considered positive, while clockwise is considered negative direction. But you can kind of go through the same rule set that we do with linear stuff, which is that um, the sign convention, doesn't matter as long as if everything's moving in the same direction, and that you can kind of set the sign however you want, as long as it makes sense. So going back, I had said before that you can take all these angular terms and turn them into linear terms. So this is the conversion for linear speed and angular speed. V equals omega r. And again, unit-wise, it makes sense. This is the meters per second. This is radians per second. We need to multiply this by meters so that we get meters per second on both sides. All right? So these are our equations so far. We have two equations to convert linear to angular values, and we have one equation to find the angular speed. One thing I do want to point out is in the note packet, you do have a few tables. You don't have to worry about filling out the tables at this moment. I'm going to kind of show you a more filled out table as we start kind of getting more terms thrown in here. All right. So here's the first question. Pause video, work yourself, and we'll go over in a second. All right. So we have a car traveling with some linear speed. This is in meters per second. We want to figure out what the angular velocity of the car's wheels are, if this is the diameter of the wheel. So what we're going to do is we're going to use this linear conversion. So we take the linear speed, we take the radius of the circle, and plug them in, and we get an angular speed of 57.5 radians per second. All right, and here's the next one. Pause video, work yourself, and we'll go over in a second. All right. So this is kind of almost a continuation of the question that we did before. So the Earth's angular speed, to figure out what the angular speed is in radians per second, well, we have to think about is what is the angular displacement and what is the time? Well, we do know in one full day, the Earth makes one full rotation. So the angular displacement is going to be 2 pi radians. And the amount of time is 1 day. So there's 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So plug that in for time. And we end up getting 7.27 times 10 to the negative 15 radians per second. For revolutions per minute, you could technically convert this. However, I would just kind of end up redoing it. It just makes life a lot easier. So a revolution is the full, almost like an oscillation or a full rotation, essentially. So it travels one full rotation, and the amount of minutes it does this is 24 times 60, because we're not going to 60 seconds, so we're not going to put that in. So we do one revolution divided by this, and we end up getting 6.94 times 10 to the negative 4 revolutions per minute. Yeah, and that's it. So we'll leave it off there. In class, we're going to continue talking about some of the more of this rotational kinematic stuff. And like I said, I'll set up that table for you to see how exactly it should be filled out. Like I said, the key thing here is to keep in mind everything that we've learned in the translational sense from units 1 through 6, and just keep in mind that the concepts carry over. It's just that we're now replacing the linear definitions with an angular definition for angular scenarios. All right. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.